Hello and welcome back. As I mentioned in the last video, we have this new quantity curvature, which is the magnitude of this dt ds, so the derivative of our unit tangent vector with respect to arc length. And right, as I mentioned in the last video, this is kind of weird because we haven't taken a derivative with respect to arc length before, but rather just the parameter that we're given for the curve. And given some curve that's parameterized by some variable t, how do we know if it's arc length parameterized or not? Well, that's the subject of a couple videos ago in 14.4. But we don't want to really have to go through that whole process every time to figure out if it's, parameterized by arc length or not, and then shifting the parameterization so it is parameterized by arc length. That's sort of a lot of work. We'd like to just have a formula. We'd like to do this once, sort of in general, and then have a formula that's going to work for all cases. So as it turns out, this is not too difficult to do. Recall, it's really going to come from the chain rule. So recall that ds dt, so the change in arc length with respect to time, is the speed at which the object moves along the curve. Or just, if we're not thinking of an object moving along a curve, but just as vector valued functions, it's the magnitude of r prime. That's ds dt. So using the chain rule, we have that dt dt. So we can take this derivative, right? We can do a derivative of my unit tangent vector with respect to time. We can figure this out. Well, this is dt ds. So if we first take a derivative with respect to arc length and then multiply it by this scalar derivative, ds dt, that's the chain rule. And what we get out is, well, we have dt ds here. That's what we're after. And ds dt, which is just speed, which we can get a hold of. So I'm going to write this as dt ds, again, this is the quantity we're after, times ds dt, which is my velocity, magnitude of my velocity. So dt ds, solving for what we want a formula for, dt ds, this is 1 over magnitude of velocity, or magnitude of the derivative, times dt dt. So now we have this thing that we're after in terms of this thing we can get a hold of and this other thing that we can get a hold of. So this is our best way to calculate curvature. Again, well, so this is dt ds. We want curvature, right? Remember, curvature with respect to arc length is magnitude of this, magnitude of dt ds. Excuse me. So here we're talking about magnitude of this. So this is going to be 1 over magnitude v times magnitude of dt dt. And so this is k of s, so we'll have to input the time value that corresponds to this point along the curve. So we'll get more into that later, but this is the idea, is these are the two things we need to compute in order to compute the curvature. Let's look at an example. And this one, we're going to compute the curvature of a line. So here is our standard line, right? Remember, x naught, y naught, z naught. This is our fixed point on the line and our direction vector a, b, c. So before we do this, imagine what this line looks like, right? It's some space, some line in space. What do you think the curvature is? How does the unit tangent vector change as we move along this line? That's what you should think about before even attempting to calculate this. Do you have a guess of what the curvature is? So the guess should be, I mean, it's a guess, so it's okay if it's wrong, but it should be 0, right? The unit tangent vector is always going to point in the direction of this a, b, c, of this direction vector. It's never going to change direction. So our curvature should be 0. Let's work that out. So what do I need for curvature? I need 1 over the derivative. So I'm going to need the derivative, and then I'm going to need to compute the unit tangent vector and take a derivative of that. So let's break this down. Let's find r prime first. That's a good way to start. It's just finding the derivative. We've done this one before for a line. It turns out to just be the direction vector. So magnitude of this, so this is, we could also think of this as like velocity, right? Magnitude of the velocity vector is square root of a squared plus b squared plus c squared. I can now compute my tangent, my unit tangent vector. So briefly recall how to compute a unit tangent vector. It's in the direction of the tangent vector, but with unit length. So that means we divide by the magnitude of the unit tangent, or of the tangent vector. So this unit tangent vector is 1 over square root a squared plus b squared plus c squared times the vector a, b, c. That's my unit tangent vector. And let's take a derivative of this now with respect to time, because we need dt dt. So then dt is, well, let's see, what's the derivative of this with respect to time? Oh, everything in here is a constant. So this is not changing, again, which is exactly what we could have predicted, right? We know that the tangent vector is not going to change as we move along a line, and so this derivative of the tangent vector is the 0 vector. dt is 0. The magnitude of that, dt, is the 0 scalar. So the curvature function k is just always 0. So that is, any line through space has 0 curvature, which is what we could have predicted. But this is the calculation that confirms that. So lines have no curvature. So let's do another example of something that does have some curvature, and that's a circle. So we can imagine a circle. Maybe I'm going to briefly sketch a circle, but maybe we have a picture in our heads of what a circle looks like, hopefully. Here's my circle, and it probably looks a lot better than my drawing. What is the curvature of this curve as I move along it? Right? So think about, how does the unit tangent vector change as I move along this thing? What do you predict for the curvature? Is it variable? Is it 0? Is it constant? What sort of things can you predict here? So come up with your prediction, and then let's actually calculate this. So again, I'm going to follow the same steps I did with the last one. I'm going to first compute r prime of t, because I know I'm going to use that. This is a derivative we've done before. It's minus r sine t, r cosine of t. I can compute the magnitude of that, r prime of t. Magnitude of r prime of t, so that's what? Square root of r squared. I feel like we've done this so many times, but I like to, kind of go through it every time. R squared cosine squared t. It doesn't take much time to redo this. But remember, we always get this idea when we're dealing with a circle that sine squared plus cosine squared is 1, so we just get r squared under the root, and we just get r out. So that is, the magnitude of the tangent vector is the radius of the circle. Remember, this is also the same as magnitude of velocity. All right, so there's my velocity. We also need the unit tangent vector. Let's go ahead and find the unit tangent vector t in terms of time. So this is 1 over v times r prime of t. Remember, this is always 1 over the magnitude times the velocity vector. Right? This is the same thing as v. So this is 1 over r times minus r sine t, r cosine t. We can bring that 1 over r through, and we just get minus sine t cosine t. So that's our unit tangent vector, right? It points up here, over there. We've gone through this example before. So unit tangent vector, and now we can take a derivative of this with respect to time. So derivative of my unit tangent vector, how does this thing change with respect to time? It's a derivative of this quantity here. So that is minus cosine t, and then minus sine t. And remember, this is the negative, it's not quite the negative of r of t, right, is it? Because we've now haven't just taken two derivatives, we're not just looking at acceleration, at which point we would get minus r, but we're looking at the derivative of the unit tangent vector, just how it's changing. So we don't get quite minus r. So there's dt dt. And then remember that curvature, k, is not just dt dt, but 1 over v times the magnitude of dt dt. So let's go ahead and we have all those pieces now. Over v times magnitude of dt dt. So 1 over v, v was r, so this is 1 over r times dt dt minus cosine t minus sine t. And we want the magnitude of this. All right, the magnitude of this is, all right, it's going to be square root of cosine squared plus sine squared. That's just 1. So yeah, I'm kind of jumping the calculation here because we've done it so many times. Cosine squared plus sine squared is 1. The square root of 1 is 1. So this is just 1 over r. And let's analyze this a bit. So curvature, remember, in general is a function. I put in a point along the curve in terms of arc length or in terms of time, and out comes the curvature at that point. What we're seeing here is that the curvature is constant. So curvature, one of the big takeaways here is curvature of a circle is constant. And more specifically, the constant is 1 over the radius. So this should make sense. Remember, higher curvature means a tighter curve. Smaller curvature means a flatter curve. So if my circle has a huge radius, if it's a giant circle, I'm not going to be turning as much. Right? My curvature should be smaller. And that corresponds to this. This is telling us exactly how those relate. Is curvature is very high. As r goes to infinity, curvature goes to 0, and we approach a straight line, curvature of a straight line. As r goes to 0, or I really don't want to think as r going to 0, but as r gets really small, the curvature is going to get very, very large, right? Compare going around in a car in a circle that looks like this. So really, really tight circle. That's going to be tough to do. We're going to need a lot of friction for that. That's a lot of curvature. Compare that to the curvature up here, where we might be able to go without turning as much. So that's the idea. Okay, that's it for this video. We've now computed curvature of two different classes of curves, straight lines and circles. Remember, straight lines have 0 curvature, constant curvature, but 0. And circles have constant curvature, but positive curvature.